Behind me is the entrance to the jet tokamak, which is currently the world's largest fusion reactor. It routinely makes plasmas of more than 100 million degrees, 5 times hotter than the centre of the sun, and today is the hottest place in our solar system.
A global industrial revolution is underway.
Yes, we have a technological challenge for our environment, for the well-being of the population of the planet, for civilization.
Driven by passionate, dedicated individuals intent on shaping a new world.
I do it because I look at my kids, and I honestly am convinced that this is the way.
A cleaner world.
There is a way forward other than burning fossil fuels out of our funnels.
A greener world.
This wind farm is producing more hours of power into the grid than all wind farms in the UK and probably in the world.
What we've done in the past is not going to solve these challenges. We need to find new ways, and I think the only way to do that is to bravely step forward and implement technology.
Together, they are pushing engineering to its limits to create extraordinary machines that can protect our planet for the future. It may be the greatest technological challenge ever undertaken by humankind. The quest to produce the ultimate energy solution, a reliable source of clean power.
Windmills are great, solar is great, but they don't work when the wind's not blowing or the sun's not shining.
So what if we could create here on Earth our very own version of a star? A machine that makes power from nuclear fusion.
When fusion is working, it will allow us to have baseload electricity, replacing all coal gas stations without producing any greenhouse gas emission. The potential for fusion is massive.
So fusion offers humanity an unlimited source of energy.
But there are big challenges. Most of those challenges are actually engineering challenges.
It has taken 70 years and a truly global effort, which has seen science transcend the boundaries of Cold War politics in a common goal. But so immense are the challenges, the goal of a power-producing fusion reactor has so far remained elusive and out of reach. It's going to require the mastery of extraordinary temperatures, the creation of magnetic fields eclipsing anything that has gone before, and the ability to sustain both for long periods of time.
For me, in terms of the world's energy needs, it's not a matter of if, but a matter of when for fusion.
For years, the attention of thousands of scientists and engineers across the globe has been fixed on crucial tests being conducted at this former military airbase in the UK. The research being carried out here is pushing the boundaries of the science and technology that underpins the whole concept of a fusion reactor. If successful, it has the potential to change the world.
Every day is a daily challenge, and we are doing first of a kind all the while. So every day is an exciting adventure on the way to a very important goal for the whole of humanity.
But these tests are just part of a much bigger story. For over a decade here in Provence, France, an immense construction project has been underway. It's here, over a few short months, that pieces of the most complex technological jigsaw ever created will be assembled. Costing $22 billion. It'll be the most expensive scientific experiment in the history of mankind. Its name, ITER, the International Thermonuclear Experimental Reactor. Nothing of this size and scale has ever been attempted before. The 42-hectare platform is 400 meters wide and covers an area comparable to 60 football fields. If successful, it will form a new blueprint for the world's future energy production. A giant machine that makes use of a process at the subatomic scale. A process which provides the energy for the building blocks of life. Fusion.
Everything that we see here is a result of a supernova of an ancient star. And that ancient star in that supernova process occurred by the fusion reaction. So as a scientist, I think it's fantastic because we're developing and controlling the very essence of the building blocks of nature.
If you could get close enough to the sun to peer inside its core, you'd see atoms of hydrogen joining together or fusing, releasing huge amounts of energy in the process. The source of energy within an atom comes from what holds it together. It's known as binding energy. So if you want to break one apart, you need a lot of energy to do it.
In the sun, because you have this enormous gravitational field, the hydrogen that's in the sun is compressed to very high pressures and temperatures to the point where when they collide, there's a significant probability that they'll fuse, they'll stick together. They stick together in pairs until you get helium. The helium has slightly less binding energy than the hydrogen did to begin with, and that difference in energy is released. It's released as heat and energy of the products and as light that we see from the sun or the stars.
Every second, the sun consumes about 600 million tons of hydrogen, releasing 500,000 times more energy than is consumed on Earth in an entire year.
The sun works because it's so big, but it's incredibly inefficient. A meter cubed of the sun actually only produces 30 watts of energy of heat. You and I actually produce more heat than the sun does per cubic meter. So the sun only works because it's absolutely enormous.
Harnessing the power of nuclear fusion has often been referred to as bottling a star. But in reality, our version of fusion will need to far exceed what a star can do.
The sun uses the lightest element known, hydrogen, to fuse together. If we actually use slightly heavier versions of hydrogen called deuterium and tritium, we can make that process happen much more quickly, much more effectively, and that is the process that we plan to use on Earth to actually recreate those fusion reactions. It's a good job the sun doesn't use those fuels, because if it did, it would have burned out in less than 1 second, rather than the 5 to 10 billion years lifetime that the sun actually has.
Fusion is all about creating a superheated, electrically charged gas known as plasma. To achieve this, you need 3 things: temperature, time, and containment, all of which create huge challenges. Firstly, how do you create temperatures of over 100 million degrees? Secondly, how do you keep the charged nuclei together long enough for them to fuse? And lastly, once you have achieved the first 2 and created plasma, how do you contain a substance that would instantly vaporize any known material it touched? The teams here at Culham and in France believe the solution lies in a concept first conceived of in the Soviet Union in the 1950s, a tokamak reactor.
So this is JET. This is the Joint European Torus. It's a tokamak. It's a device that uses a magnetic field to confine a plasma at very high temperatures in order to make nuclear fusion. there's a system of magnets on JET, one system wound around the torus this way and one system wound around the torus that way, that keeps the plasma in the center of the vacuum system away from the walls and allows you to raise its temperature to this 100 or 200 million degrees C. It's donut-shaped, it's toroidal, because the magnetic field confines the plasma from moving across it, but it has no confinement properties along the magnetic field. So you can't have ends in the field, and the way you avoid having ends is you twist the magnetic chamber into a torus. If you go anywhere in the world and you look at magnetic confinement devices, you'll see different kinds of donuts. This one's called a tokamak. JET is a high vacuum system, which we pump out at the start of every experiment, and then we inject a small amount of gas into the chamber of deuterium and tritium, which are the two isotopes of hydrogen we use to make fusion. These are then ionized using a very high electric field that is generated around the tokamak. Once they're ionized, they conduct electricity, and the currents inside there are up to about 4 million amps. At those very high currents, you heat the gas and turn it into a plasma.
So we've electrically charged and heated the gas to create plasma. But at this stage, it's a mere 10 million degrees Celsius, which might work for the sun, but without the benefits of the sun's size and gravitational field, it's just a tenth of the temperature needed to create energy-producing fusion here on Earth.
So what do? We add additional heat systems for heating the plasma, for boosting the temperature of the plasma by another factor of 10 or so. There are two such additional heating systems on JET. One is a resonance system, a bit like a microwave heating food in your kitchen. This system inside JET is capable of putting 8 to 10 million watts of power into the plasma.
To give you some comparison, that's something like 10,000 times the power of a typical microwave oven.
The second additional heating system is this large system here, where we inject very high energy neutral atoms into the plasma. Neutral, so they don't see the magnetic field. This system and its sister on the other side of the machine are capable of putting more than 30 million watts into JET. The combination of the two heating systems lets us boost the temperature up to those we need in order to make fusion.
But the problem is that as large and sophisticated as JET is, creating the plasma requires so much power that the reactor doesn't actually generate more power than is put into it. Scientists often compare it to lighting a fire. You need a match to get it started, but ultimately you need that fire to keep itself going. The problem is to create enough plasma to keep the temperature up, which is what is called burning plasma. And that's where ITER comes in.
So ITER is the next step. And so we're building off of all the knowledge of these existing machines to be able to go to the next step, and where we put, for every 1 watt we put in, we would be able to pull out 10 watts from this fusion reaction.
This has never been done before. We have excellent calculations that have been validated by experiments at the level we can do them now, but nobody's gone to the level that ITER and a future power plant for fusion would have to go to, which is dominant self-heating. And so that's one of the really big physics challenges that's exciting, is this will be the first time we go to the place where we have a true burning plasma.
And that burning plasma can be used to heat water flowing through pipes, which in turn can be used to power turbines, just like in a conventional power station. Just 250 kilos of deuterium and tritium could power 1 million homes for a year. To do the same thing, a coal-burning power station would require 2.7 million tons of coal. But while deuterium is readily abundant and can be distilled from seawater, tritium, a vital part of this technological jigsaw, is a different matter.
Deuterium and tritium are two different kinds of hydrogen. Hydrogen is the first element in the series in the elemental table. but it comes in 3 different flavors. Protium, which is the one that is normal. More than 99% of the hydrogen on Earth is protium. Deuterium, or heavy hydrogen, and tritium, which is heavier again. Tritium is radioactive. It decays with a half-life of a little over 10 years, so there isn't very much on Earth.
In fact, the total world stockpile of tritium is only around 20 kilograms, mostly produced by reprocessing spent nuclear fuel from conventional fission reactors.
So the way we get around that is we're going to make our own tritium. We're going to put lithium into the blanket of a fusion reactor. The neutrons that are produced by the fusion split the lithium and make tritium. In that way, we make more tritium than we burn. We feed the tritium we've made back into the reactor, and we have something that's effectively using deuterium and the lithium as a fuel. Lithium you can mine. It's available on Earth in deposits. There's also lithium in seawater. Because the deuterium and the lithium could potentially come from the seawater, everyone has access to it.
This potential for a reactor to effectively produce its own fuel from such an abundant source is just one more reason why ITER is so important. When completed, it will be the biggest fusion reactor ever constructed. Weighing 23,000 tons, it will be 3 times heavier than the Eiffel Tower. And then there's the magnets, vital for containing the burning plasma and keeping its immense heat away from the vessel walls. Each one of its 18 toroidal magnetic field coils will weigh the same as a fully loaded Boeing 747. Together with another 6 circular magnets, 48 meters wide and weighing up to 400 tons, they will exert a force equivalent to twice the thrust of the space shuttle at takeoff. And all of this in the quest to produce and control large amounts of plasma.
Hydrogen, when it gets ionized into a plasma, it's got a beautiful pink glow to it. So you have this sort of pink aura you feel like you're making a work of art and a work of science at the same time.
To create the very powerful electromagnetic fields needed to confine the plasma, ITER's magnets are like nothing ever produced before. It's a process that started 30 years ago. And heading the magnets division is Neil Mitchell, a man who's been involved in their development from the very start.
It's quite personal because, I mean, I've spent not only my career, but my life on this project. It's very satisfying to think, oh yeah, we were sketching that on pieces of paper 25 years ago, and look, it looks what it looks like. Yes, I mean, it's amazing in the last, well, particularly this year, actually, because really this year, everything is arriving on site.
The type of electromagnets Neil and his team are using are known as superconductors. These operate at incredibly low temperatures where the wires in them have no electrical resistance, meaning that once charged, the only power the magnet consumes is that needed to keep it cool.
The magnet system of ITER has got quite a lot of energy stored in it. It's around 40 gigajoules. If a gigajoule makes any sense to you, it probably doesn't. It'll certainly run several kilowatts of power for a day or 2 or 3. There's a lot of energy in the magnets, but it's not being consumed. You put it in and it's stored, and the currents just circulate forever for free.
1 gigajoule represents the capacity of about 4 long-range electric cars. So the magnet system within ITER stores the equivalent of about 160 fully charged vehicles. But who would make these extraordinary devices? Before ITER, the total global production of superconductors was only 20 tons a year. ITER's magnet system will weigh almost 10,000 tons.
The superconducting magnets for ITER are particularly challenging. I've been working 30 years in the superconducting magnet industry across the world, but I have to say the ITER magnets are by far the most complex I've been working on.
But it's not just their complexity. Their sheer size meant that those companies that did produce them wouldn't be able to transport them on existing roads.
So you need to have a factory very close to the sea.
Which is easier said than done. For CIMIC in Italy, in order to secure the ideal location, they had to take over premises already occupied by a company producing dishwashing machines.
But in the deal, there was the agreement that they had to absorb, to take on board most of the old workforce.
Now the workers are at the cutting edge of a technology that has multiple applications from CT scanners to maglev high-speed railways.
They trained first these people and then started working together. And I have to say that after 2 years, I have a team of very motivated and skilled technicians. I think a very important factor is the motivation. And I think to participate to a project for which the final goal is to produce clean and renewable energy and hopefully save the future of the planet, I think this is part of the reason why they were able to so quickly to bring up to speed these people.
Each of the 18 toroidal magnets contains almost 5 kilometers of conduction coil, each themselves containing 1,400 superconducting niobium, tin and copper strands. It has to be wound into a spiral with an accuracy akin to the thickness of a human hair. "15 kilometers of robot-controlled welding seals it into a casing. Wrapped, insulated, then vacuum-sealed in resin, these magnets also contain cooling pipes through which liquid helium will flow. The magnets will need to be kept cold for years at a time, and the temperature that will be required is minus 269 degrees Celsius, just 4 degrees above absolute zero, the lowest temperature physically possible. When the reactor is operational, in the center it will be the hottest place in the solar system. And just a few feet away, it will be 2 degrees above the lowest temperature in the universe, which occurs in the Boomerang Nebula some 5,000 light-years away. To attain such low temperatures is beyond any existing capacity. So they're having to construct the world's largest helium refrigeration unit. But to keep the cold from dissipating, the scientists then needed to find a way of insulating the reactor. The answer? A giant vacuum flask built from 3 enormous stainless steel sections known as a cryostat.
So we are now in the cryostat workshop. And so what you see here is the workshop where we are building the largest fridge ever constructed. So we are now entering, sort of crawling, mind your head, it says, into the cryostat, the upper cylinder. And it's here where you can feel, see and sense the dimension of our machine. It's going to be 30 meters wide, 30 meters high. This is just the upper third. And yeah, it's going to be a big beast.
It's easy to look at the challenges that ITER faces and assume they're all to do with science and engineering. But this project involves 35 different nations, representing over half of the world's population. On such a long-term project, governments will come and go. So how do you ensure that new leaders, often with a very different agenda and ideas on what they should be investing their money in, remain committed to the fusion dream? It has been estimated one giant company doing all this by itself could get things done a lot quicker. But that misses the point of what all this is about, giving everyone a vested interest.
Why do we have 35 nations? We always keep saying ITER has two main goals. One is to build this machine, ITER, and to prove that, yes, we can do fusion, we can generate energy by fusing atoms. This is the main one goal. But at the same time, we have all these nations on board, so we are building up, developing a fusion industry around the world.
So ITER is really the focus point of all of this research pointing to one machine, ITER, and then from that one machine, all the countries can go off and build their independent machines.
The person charged with coordinating the production of all these different components is Colette Ricketts, who previously spent 18 years working as a physicist with the team at Cullum.
So for me, the hardest thing on this project, with millions of components coming from literally across the globe, the challenge is always about how do we communicate. Can you imagine on a schedule that's 250,000 activities and milestones, how many issues are faced every day? Every day. Of all of that, what's key? What matters? And then to pick 5 things, 15 things, absolute maximum, to share with the project and say, we have to solve that problem. Simplifying what is effectively the world's largest, most complicated construction project today into human, understandable elements that I have no doubt the people here can solve whatever is thrown at them. They really know their stuff.
In an environment where so many different people from around the world, speaking numerous different languages, are working together to push the boundaries of science, one thing in particular has turned out to be of surprising importance in helping communication: the canteen.
The idea of just sitting down to eat, just gently getting on with conversation, which is exactly how the languages were designed to be used. They were never designed to be used in the classroom. They were designed to be picked up gradually by people saying, can you pass me that? Can you pass me that? I like this. Using the same simple phrases over and over again, we get people to join in, to ask questions when they don't understand something.
Conversation is different. You get expressions, you understand better in French les nuances in a language.
Coming to work at ITER is like coming to visit all the countries in the world. The countries in the world have come to visit me. It's a very easy way to travel, and it might be called lunches in English, but of course the ideas that are being expressed are coming from Chinese, from Japanese, from all the different nationalities who are sitting around the table. So I'm learning new things.
Although what is happening at ITER represents the cutting edge of the world's technology, the concept of fusion was actually first realized a century ago, when, in 1920, British astrophysicist Arthur Eddington suggested that stars draw their apparent endless energy from the fusion of hydrogen into helium. In 1934, New Zealand-born physicist Ernest Rutherford, known for his work splitting the atom, managed to achieve fusion in a now famous experiment that identified the potential of deuterium and tritium.
So if you look throughout the history of fusion, fusion has gone through ups and downs. For example, back when the scientists were first looking up at the sun to understand what the sun is and how does it work, there was a huge enthusiasm to be able to master the reaction of the sun. And soon we realized it was a complicated thing. And this has then sequenced to the 1950s, where we came up with this idea of magnetic confinement. And then there was an enthusiasm, and then it's dropped down again.
Once it's perfected, fusion power will give us an unlimited supply of energy.
If we learn to perfect it. But even the most optimistic scientists think that fusion power may not be developed for 50 years, if then, if ever.
By the early 1960s, the fusion research community was in the doldrums. Many initially promising experimental paths had all failed to produce useful results, and political will and support was beginning to wane. But in 1968, something remarkable happened.
The Russian scientists came up with a major breakthrough, and that major breakthrough was the tokamak.
It was at least 10 times what the best machines anywhere else in the world had been able to do. The results were so good that some dismissed them as down to faulty measurements. So what they did was to invite a team of scientists from the UK, who had been developing their own reactor on very similar lines, to independently test the Russian machine.
At that point, not only did the tokamak give birth on an international scale, but that was also the birthplace of an open collaboration. So this was really the hot point of the Cold War. And Russia said, hey, look, we have this result. And all the world flocked to Russia. And then from there, the Russians shared their experience. And at that time, it was complete open and positive exchange. And that's what I think is cool about fusion, is fusion has no boundaries.
One other event, which was a landmark moment in the history of fusion, occurred in November 1985. When in the midst of Cold War tensions, President Gorbachev and President Reagan met for the first time at the famous Geneva summit.
These two sat down and wanted to find out a way to move forward in a peaceful way. And one of the outcomes was that Gorbachev and Reagan decided, let's join forces and build a joint machine, an international machine that would try to solve fusion. And thanks to that, today we have ITER being built.
Over the years, that international cooperation has been well and truly put to the test. Nowhere more so than in the building of the vacuum vessel, the very heart of the reactor, which will enclose the burning plasma. It's made from 9 gigantic segments, 5 made in Europe and 4 in Korea, incorporating a double layer of nuclear-grade steel. Each segment weighs 500 tons, over twice the weight of a boxcar locomotive. Despite their enormous size, they require millimeter precision. With so many companies involved in numerous different countries, every aspect of ITER is an extraordinary exercise in planning and logistics. As almost half of all the components for the reactor are being provided by Europe, it was decided to set up a separate organization called Fusion for Energy, to enable a myriad of European companies to work together and find new production processes to create this one-of-a-kind engineering marvel.
Some of the things I like about fusion is that they're just mind-boggling. And even though I do this for a day-to-day type event, I heat plasmas, it's to some degree inconceivable to me that I can heat a plasma to 150 million degrees.
Although the main body of plasma created in this fusion process is contained within a magnetic cage, neutrons are also released. On the one hand, that's good, because they provide the heat energy. But as their name suggests, they are neutrally charged, so they can't be controlled by a magnet. They move at incredible speed. If nothing blocked their path, they would reach the moon in just 8 seconds. When the neutrons hit the wall of the vessel that surrounds the plasma, they can, over time, cause damage. So whilst building work began in France, it was vital that the team working with the jet reactor in the UK came up with a solution.
This is a photo of the inside of JET, about half size. It's twice this size in reality. And it gives you a good idea of what the inner skin of the reactor looks like. For a long time, all of these tiles on the inside of the reactor were made out of carbon. And the reason we did that is because carbon's very forgiving material. And when you're an experimental device and you want to push the limits of the experimental device, we could overheat the carbon and the tile didn't change shape. The problem with carbon is that it reacts with the hydrogen. It reacts with the deuterium and tritium is in the plasma, that are your fuel. And it reacts in such a way that it locks the fuel up inside the machine. So what do? You change from carbon to metals.
But getting metals into the reactor to test proved a challenge in itself. Because of low-level radioactivity and the need to keep impurities out, they needed to find a way of working inside the chamber without actually entering.
We are in the JET remote handling control room. This is where we maintain the inside of the reactor vessel. We need it because JET is the only machine in the world that uses the fusion fuels, and therefore it has an activation level inside the machine. So when we talk about you're not allowed to go in there, we're talking about radiation levels that are comparable to what you get from walking around for a year. We're trying not to increase the dose of any of our workers significantly above what the background level is. Well, like a lot of JET, it's all one-off. It's all been built from the ground up. It's taken 20, 30 years to develop this. It started off with technology that came to us from the high-energy physics community, but it has been developed all out of recognition since then. It's incredibly sensitive. It's possible to do things like start to screw in a volt, feel that it's cross-threaded, back it out again, put it in straight with this tool. It's possible to feel the edge of a piece of paper, that sort of a step. It's very, very sensitive. Everything is rehearsed in our training facility before it's done inside the machine, and it takes months, if not years, to get to the point where you're a fully trained operator on this system.
This highly precise remote handling system meant they were able to remove and analyze samples from the wall of the chamber no bigger than the point of a pin. After much research and testing, they decided on two metals. The first was beryllium, a very light, unreactive metal used to make, among other things, missiles and aircraft.
Beryllium we use in the main chamber because it's next to the high-temperature fusion plasma. Here, we have the 200 million degrees that you need in order to make fusion happen. As powerful as the magnets are in JET that make this cage that keeps the plasma away from the wall, there's always some leakage. And in a tokamak, in JET, we arrange it so that those losses are diverted down to the bottom of the machine.
Here they use tungsten, which, although slightly more prone to react with hydrogen than beryllium, is one of the toughest metals found on Earth.
In the bottom of the machine, the plasma is much colder. It's only 20 or 30,000 degrees. At those sorts of temperatures, with a high melting point material like tungsten, the plasma can touch the wall.
But changing the lining of the vacuum chamber was no small feat. It meant replacing 4,000 tiles, all of which had to be done remotely. The knowledge gained here at Culham has meant that ITER's remote handling simulator has already been built, meaning trained operators will be ready to go as soon as the reactor is fully assembled. Whilst a huge international effort has been going into building a viable energy-producing tokamak by 2025, there are some in the scientific community who believe we should be pursuing a very different route to fusion. In the 1970s, scientists began experimenting with powerful laser beams to heat a sphere containing hydrogen isotopes, to the point where they would implode with enough force for the hydrogen atoms to fuse.
Here's how it works. An ultra-high-powered laser would fire its light beam at a very small pellet dropped into a target chamber. The pellet would be hit from all sides at the same time, its outer layers vaporizing away, the inner core compressed.
This implosion mimics the huge gravitational force that stars use to create, then contain, the fusion process. It's called inertial confinement fusion. But as with everything to do with fusion, life is never that simple. To momentarily implode hydrogen pellets smaller than a sugar cube requires a laser that is 10 stories high and covers an area twice the size of a football pitch. But the inertial confinement story doesn't end there.
So this is a pistol shrimp, and if you're wondering what this has got to do with fusion power, then that's a very good question.
Nicholas is co-founder of a company called First Light Fusion, who was inspired by a small but remarkable crustacean to look at creating inertial confinement fusion in a way that requires only a tiny fraction of the energy of a giant laser. The pistol shrimp snaps its claws so quickly that it creates a sonic shockwave that can stun or even kill its prey. The speed of its snapping jaws creates a gas bubble that collapses in on itself. As this cavity implodes, the air and vapor inside is heated to such an extent that a plasma is momentarily formed, which has been estimated to have a temperature close to that found on the surface of the sun. It's the only known example in nature of internally confined plasma other than a supernova.
With the shrimp, the plasma is whatever happens to be in the bubble, which is a bit of gas and a bit of water vapor and so on. For us, to make this into a scheme for fusion power, inside the bubble you put deuterium and tritium, and it's the deuterium and tritium which are getting heated by that collapse process. Instead of clicking the claw, what we use is a high-velocity projectile. So this is what our targets look like now. So this is our replacement for the bubble that the shrimp creates. If you look at one of our simulations, this is the simplest possible one, with just one bubble by itself. You can see there's a huge amount happening. But one of the key things is the pressure wave, which is moving in. When it hits the top of the bubble, it causes it to turn inside out, and it forms a jet, which moves across the bubble and then hits the back wall of the bubble. The key thing is that actually that jet moves faster than the projectile. It compresses the fuel inside, the deuterium and tritium, and for a tiny fraction of a second it gets to enormous temperature and density, and it will give a pulse of energy out, a pulse of neutrons out. And each one of these targets will release about the same amount of energy as an entire barrel of oil. And that's how the power plant works, is you put one of these into the power plant, you hit it with the projectile, it releases some energy, you have to capture that energy, and then you have to do it again at some frequency, and that's how you get power out.
Having originally experimented with a gas gun, they found that although they could launch a small projectile at 15,000 miles per hour, it just wasn't fast enough. So they moved on to electromagnetic launchers, which use a huge pulse of energy.
Okay, so this is machine 3, our latest pulse power machine, an electromagnetic launcher. In here we've got 192 capacitors. We charge these up to 100,000 volts. And when they're fully charged, we've got 2.5 megajoules of stored electrical energy.
Which means that this machine has the ability to generate an incredible 14 million amps.
Okay, so it's much easier to get a feel for M3 from up here. We've got the 6 limbs, the 6 banks of capacitors arranged around the outside. When the switch is closed, the current flows down each of these limbs and into the center section. So what you can see here is our vacuum chamber, which is just being assembled. It'll have a lid on it, it'll be sealed, and within that is where our load section goes, where all of this power converges. The load is this circular disc here, where the 14 million amps flowing, they converge in this very centerpiece down the middle here. And in there, there's a very small disc which bursts free. It's machined out of one piece. It's right at the bottom of that sort of chimney section. And that's where the current's flowing. And that piece breaks free and it flies up that chimney, and that's where it hits our target. So the real challenge is getting the energy into the load as quickly as possible. And to achieve that, we have to close the switches in tens of nanoseconds, that's billionths of a second. Once the switches are closed and we're discharging the whole machine in 1.5 microseconds, and for that instant, the power in the load is greater than the US national grid. So the projectile can reach speeds up to 20 kilometers per second. And to give you an idea of that, it would be London to New York in about 4 minutes. So it's really moving when it gets to the top of that chimney. A pilot will pass out at around 9G. This is experiencing around 1 billion G.
But as impressive as the projectile mechanism is, the main focus of the team is to create the optimum interior of the small target. This means experimenting with different sizes and numbers of bubbles, which all interact with each other to amplify the shockwave.
The benefits of our approach is the rest of the power plant is so much simpler. It's nearly all existing technology, in fact. So if we can make this work, we have a much simpler pathway to fusion power, which is what matters.
Okay, short time. Check set voltage and current. Siren on. Valves open. HV on.
Beginning charge to ±70 kV. 10 kV.
Diagnostics.
60 kV. Approaching full charge.
HV off. Send trigger.
As the lid of the vacuum vessel is removed, the evidence of the huge, albeit fleeting, creation of energy is immediately apparent. But while this machine is a good way of testing individual fuel cells, a working power plant would need to provide a constant stream of such energy pulses.
Our current thinking for, let's say, repeating this process of impact between projectile and target is to inject the target potentially only by gravity down a tube, and then that target would be chased by a projectile which has much higher velocity. For the projectile, the target is as if it was stationary, in fact. You need to imagine this event being repeated every 20, 30, 40 seconds. And basically, every time there is an event, you get a burst of energy. In order to convert fusion energy into heat, you need a device called a blanket. In our reactor concept, those blankets are falling curtains of liquid lithium, which serve multiple purposes, in fact. One is to convert the fusion energy into heat, which can then spin a turbine and generate electricity. But the reason why it's lithium is also because that allows us to breed or to produce the tritium that we actually then have to feed back in the process because it's one of our components of the fuel.
Fusion can be done, and it will be done, and it can be done in time to solve climate change. Right, if we're going to get to net zero in 2050, we need 10 plants on the grid in 2040. To get 10 plants on the grid in 2040, we need 1 plant in 2030. To get 1 plant in 2030, we need to prove the physics works in the 2020s, in this decade. And we can get there. Even the big mainstream projects can get there. ITER is going to have first plasma in 2025. But in principle, they can do it. They can get there. And that's the timetable we have to hit. It is possible. It's going to happen.
Back at ITER, after a decade in the making, the large components are due to start arriving from all over the world. But in all the years of planning, there is one thing that even the brightest minds in the business have not anticipated: a world in lockdown. For Alain Beculet, the head of engineering and the man charged with overseeing the assembly process, it was just one more challenge in a long line of challenges.
So how did ITER cope with the COVID-19? It's really a moment when we have discovered new or other ways of working, and we very likely will take lessons out of that. So the number of people working on the construction side was cut by 1/3, but we still could carry on the main activities. On the engineering, corporate, science and operations side, everybody went home, everybody worked from home, and people carried on designing and working from home. In a sense, we are used to it because the ITER organization is spread around the world, so we are used to work remotely. And as I said, we are now taking lessons also out of that and trying to create what we are calling now the new normal, because in a way it works.
If visible proof were needed that progress is being made, it doesn't come much bigger than this. The 3 massive sections that make up the cryostat have been completed. The base alone weighs 1,250 tons. But building a reactor out of such huge sections created yet another technical challenge. How do you first move them, then assemble them in their final resting place in the reactor hall? This unprecedented problem required an unprecedented solution. A vast assembly hall has been created next to the reactor building. Within it, 2 newly installed cranes, able to lift 1,500 tons, will carefully carry each unique and precious component to what is known as the tokamak pit. It's a hugely symbolic moment, as it represents the start of the assembly process.
It's really the precision that we want to have all along the movement. So this element, this huge plate, is moving centimeter per centimeter.
It is crucial that the cryostat base is positioned in exactly the right place. Around it, the rest of the reactor components will be assembled. Components which have been a decade in the making. Components which have been designed to be millimeter perfect in order to fit together. No ifs, no buts. It has to be right.
If we are not sure that it's perfect, we have to come back immediately to this imperfection. Otherwise, if we let imperfections develop, then at the end of the day, for sure, it doesn't work. It is the Pisa Tower, if you want. If you don't pay attention, at the end of the day, you have this. Okay, we want something that is perfect.
Having arrived over the tokamak pit, it now needs to be lowered. It's a painstaking process which moves at an almost glacial speed.
And there are controls all the time. It's real-time control, the position, the locations, and so on. If you are in front of it, you almost don't see it moving. It's controlled millimeter per millimeter. This is really impressive.
But with so much of the huge reactor being constructed off-site, there are still over 200 giant shipments, some of which weigh over 400 tons, that need to make the 100-kilometer journey from the port. However, when they did the calculations, they realized there was no route that could cope with the massive dimensions. And so roads have been widened, intersections changed, and even part of a cliff removed.
To the question, are you relieved when it comes? Of course, but more than relieved, we are so happy.
Now the assembly can begin in earnest. Although it will be 5 years before the giant reactor fires up, to the thousands of scientists and engineers around the world who have been working on fusion for over half a century, this is acknowledged as a landmark in the future of fusion energy.
I think, for me, this is the end of a very long road. It's quite a matter of some pride that we actually managed to do this, and it's all come together and it's here.
But for COVID-19, today would have seen a celebration attended by the world's leaders and huge international press coverage. But in some ways, the small gathering of scientists who have made it here today is far more apt. They represent people that have devoted a lifetime in pursuit of this goal, and they are keenly aware that they are passing the fusion mantle to the next generation.
Well, yes, I'd like to manage to keep going for another 5 years and actually turn it on to check that it works.
It's an enormous challenge for our generation, for the generations to come, and I hope that people will be excited about what we're doing here at ITER, support it, but also get involved themselves and go into the engineering disciplines, go into the scientific disciplines that will be necessary for that reality to be true for the planet.
I do feel like I've added a contribution along with thousands of scientists before me and thousands of scientists in the future, that we together have provided an energy source.
Why do I do it? I do it because I look at my kids and I honestly am convinced that this is the way. This is the way to solve the future problems we have. In addition to renewables, yes, it's a combined energy mix, but there's nothing else on the table that offers this amount of energy benefit for such a low impact on the environment.
I met some of the engineers working on the Apollo project when I was a kid, and I thought, wow, it must be really cool to work on the Apollo project to put the man on the moon. It's the same thing. To me, it's just the ability to say, I helped build this thing. I helped humanity overcome our energy crisis. And that just seems like, wow, that is really cool.
Anyone who has spent time by the coast will have witnessed the raw power of the ocean. As tides rise and fall twice a day, vast amounts of water swirl around the Earth. This is a huge energy source that's currently largely untapped.
500 million tons of seawater an hour go through these gaps. Those are titanic forces.
An estimated 3,000 gigawatts are available to be harvested globally, enough to power a third of the Earth's homes. Yet compared to wind and solar, the technology needed to harness tidal power is still in its infancy, and the challenges of operating in these environments are enormous.
The ocean can be cruel at the best of times. And then you'd move that water at 10 knots, which is like a 100-knot wind. So you can imagine that's a very, very, very aggressive environment for these machines to survive in.
Yet there are teams of engineers around the world determined to take on that challenge, to help the planet. Their goal is to build machines that are tough enough to not only survive these conditions, but thrive in them.
The wind's been harnessed, solar's been harnessed. We're trying to bring new industry to the world.
Although these turbines are destined to be submerged below the sea, the vast energy they're designed to harness owes its existence to a phenomenon high above our heads: the movement of celestial bodies through space. The moon is closer to the Earth's surface than it is to the center of the planet. That means its gravity pulls slightly harder on the ocean nearest to it than on the rest of the Earth, creating a bulge of water. The moon's gravity also acts more strongly on the center of the Earth than on the furthest ocean, creating another bulge. These two swells of water appear as high tides at the coast. As the Earth spins, both of them move around the planet's surface, so that most places experience 2 high tides a day and 2 low tides. Twice a month, when the Earth, Moon, and Sun align, their gravity is combined, and you get even bigger tides, called spring tides. The rise and fall of the Earth's seas and oceans represents a vast amount of energy. People have harnessed that power since time immemorial. and a handful of tide mills still make flour today.
A tide mill has been here for 850 years. Grain would be grown here, collated at this mill, and then processed, and then it could be easily shipped away.
Dan Tarrant-Willis knows the rhythm of the tides as well as anyone.
The tide affects my life in a beautiful way because I kind of live by the tide. So I know I'm working if it's low tide. If it's not low tide, I'm not.
Behind the building is a mill pond. When the tide comes in and the water level rises, the pond fills.
It has a one-way valve in it, so as the water rises, it fills the mill pond. That fills up to the height of the tide. We then wait until low tide, and at low tide, we empty the water that we've captured at high tide underneath our wheel.
The wheel is connected to a shaft, which turns a set of millstones.
That turns at about 50 RPM, which is perfect for turning wheat into flour. There are 2 low tides in each 24-hour period. I've basically only got 2 hours a day that I can mill.
During the Industrial Revolution, tide power gave way to coal-driven steam power, which was available on demand. After that, tidal technology almost disappeared, with a notable exception. In 1966, a tidal barrage was built across the mouth of the Lorentz River in France that still operates today. As the tide rises and falls, water pours through 24 turbines, generating enough electricity to power the nearby city of Rennes. But the structure was very expensive to build, and it damaged the estuary's ecosystem. Interest in tidal energy reached a low ebb. Yet recently, engineers are starting to look to the ocean again. The climate crisis has given fresh impetus to finding clean energy sources to replace coal and gas-fired power stations. And tidal energy has a crucial advantage over wind and solar power.
The greatest thing about the ocean is its dependability. We know that the tide comes in and out. We have tidal charts going back hundreds of years. That's always going to be that set amount of energy, that time of day in a tide, and we can rely on that. That's the biggest upside of what we try to do with marine energy.
Drew Blaxland of CIMEC Atlantis has been working for decades towards a new way to capture the tide's power. Now it's being put to the test. June 2016, the AR 1500 tidal turbine is being assembled at a research centre in northern England.
This is a very exciting moment for myself and everyone in the team. This is the world's first commercially viable tidal turbine for the world's largest tidal energy array in the world.
It's designed to generate power in the open ocean. The machine looks like a wind turbine that sits on the seabed, 100 feet below the surface. It's driven by tidal currents. These are created by water flowing towards parts of the sea where the tide is rising. When the tide changes, the turbine rotates to catch the flow in the other direction. The current drives the rotor around, turning a shaft which goes inside a waterproof casing called a nacelle. There, a generator produces electricity, which flows back to shore through an undersea cable, where it connects to the grid. Each unit is designed to generate enough electricity to power 650 homes, day in, day out. It's much simpler and cheaper to build than a tidal barrage, and should have less impact on the environment.
The greatest thing about what we do is the turbines turn up off the back of a ship, lots of activity, this beautiful, pristine environment, and after we leave, it's still a beautiful, pristine environment. You don't know we're there, and there's now power being generated.
But before disappearing beneath the waves, the turbine must first prove itself on land, without its blades. The team connect the shaft to a test rig, to simulate the extreme dynamic loads it will experience under the sea. Over the course of 6 weeks, the powerful test rig drives the shaft with the same force as it will experience under the full tidal flow. But as well as turning the shaft around, the test rig can apply hundreds of tons of force, pushing it back and bending it to the side, just like the turbulent ocean. Despite the punishing loads, the powertrain, bearings, and control systems all work perfectly.
It's an absolutely huge milestone for us, and the feeling is absolutely excellent. It's the kind of thing that you spend your whole career building up for, is these moments when you can say that all that hard work was really worth it.
The turbine's ultimate destination lies off the northern coast of Scotland, where the tides are legendary. Orkney, a remote windswept archipelago. The raw power of the ocean around the islands is breathtaking. For 15 years, Neil Commode has run a marine test site for wave and tidal energy devices here.
There's a huge amount of tidal energy in the waters just around Orkney. It's estimated it's something like 20% of Europe's tidal energy are here in the waters around these islands.
Traveling around the islands can take much longer at certain times of day than others, depending on which direction you're heading.
Well, it appears that we're powering along at a brisk 8 knots or about 10 miles an hour. But actually, if you look at the side, you can see we're not moving at all because the boat is having to work against the tide.
Although the vessel is moving rapidly through the water itself is flowing at roughly the same speed in the opposite direction. Despite its appearance, the water is moving faster than most whitewater rapids. The reason the flow here is so fast is because of Orkney's unique position.
Orkney has got 2 bodies of water around it. It's got the North Atlantic and it's got the North Sea. And the North Sea at the moment is higher than the North Atlantic, so the water is running downhill towards the North Atlantic. And 6 hours later, it all turns around and goes back the other way again.
As the water pours from one sea to the other, it's forced into narrow channels between the islands, making it speed up even more. When the tide changes, the currents slow down and stop before starting to flow back.
500 million tons of seawater an hour go through these gaps. Those are titanic forces.
These powerful currents are known as tidal streams, and they're a huge potential source of clean power.
We're standing effectively on a river of energy that's roaring past us, that's driven by the position of the moon and the sun, and that's never ending. So if we can tap into the currents and the energy that's in this water, that gives us, frankly, an inexhaustible power supply.
Experts estimate tidal streams in places like Orkney could one day meet 1/5 of the world's electricity demands. The stretch of water with the most potential here is the channel between the islands and mainland Scotland, the Pentland Firth. Here, the water flows so fast, it's been called the Saudi Arabia of tidal stream energy. There's enough power to generate a vast 4.2 gigawatts of electricity, more than the world's biggest wind farm and solar farm combined.
The flow in the Pentland Firth is fantastic for tidal turbines. You have the North Sea and the North Atlantic, and the tidal exchange between the two, you get tides up to 10, 11 miles per hour, which is great for tidal generation. It's 100, 120 feet deep, 30, 40 metres. You really couldn't ask for a better place to do tidal and reasonably close to shore as well.
CIMIC Atlantis will deploy 4 turbines here at first, with plans to scale it up to an array of hundreds of machines in the future. The first AR-1500 turbine has arrived, and its 3 30-foot-long blades are assembled into the rotor, spanning an area the size of a tennis court.
The bigger your rotor is, the more power you're able to generate, the more yield you can take for any given megawatt.
With the blades on, the machine stands 78 feet tall.
It's 4 to 5 stories high, it's 150 tonne plus the foundation, it's 1,300 tonne of steel. It's, it's a big beast.
The huge structure must be transferred to a ship to sail out into the Pentland Firth, one of the world's most challenging locations.
The tide is roaring along for most of the day, a good 20 out of 24 hours, up to 10 miles an hour, depending on the site. And you've got to get in there in the 4 1-hour maximum hour periods to do your work. So you've got to find ways of designing your equipment and everything you do for that little tiny period of time. It's almost military precision. You need to go into it almost like you're planning a battle, and you go out, jump out of your trench, do your thing, and then scurry back in your trench for the next 4 hours and have another crack.
A high-precision operation like this needs a sophisticated dynamic positioning vessel. It uses satellite technology to remain stationary despite the currents. But the water here flows so fast that the operation must still be completed in the short window of slack tide, when the current slows down before it changes direction.
So what we've actually done is we've installed cameras in the bottom of our turbine. You've also got an ROV, a remote operated vehicle, which is a robot effectively that can watch the turbine as it comes down. Imagine that is the top of a foundation. Big pole, 2.5 metres diameter, sticking out of the seabed, and you're aiming for that. And that's the female connection. The bottom of the turbine, this is now coming down from the top, is the male connection.
The tide has now turned, and the water's starting to flow. It's already pushing the turbine out of line. In a few minutes, the current will be too fast for the vessel. But if they abort, it means a 6-hour delay.
Time is money. Every day we're offshore with large vessel assets costing, 50,000 a day plus. So time is absolute critical offshore.
The team have one last chance to make the connection.
The next trick is you don't even have to get it that close. You have to get it within tolerance, and we have special features on our stabbing system that allow it to turn on its own as it comes together. And that's basically like a bayonet fitting that brings it together. Once it's together, that's it. There is no extra fasting, there's no clamps. It's 150 tonnes, about 90 tonne underwater, because you lose weight as you go in the water, and it sits there just on gravity.
3 more turbines are also taken out and installed in the Pentland Firth. A project called Maygen that can power 2,600 homes with green electricity.
So at the Maygen site, we have 4 1.5 megawatt turbines. That's reasonably small in comparison to wind, but it's the start of tidal arrays.
As well as installing the turbines quickly, the same system can also be used to retrieve them for maintenance. But they still need expensive equipment to do it. So if the turbines need many repairs, the mounting costs could be prohibitive. On the west coast of Scotland, a different tidal device is being developed to avoid that risk. Connell, on the shores of Loch Etive. During spring tides, conditions here draw kayakers from around the world to brave the famous tidal race called the Falls of Laura. Evidence of the plentiful tidal energy available.
The water flows up into Loch Etive, and then it comes out in a great rush past the Falls of Laura. And it's almost like a horizontal waterfall where it really rushes through there at a huge rate of knots.
Jason Heyman is CEO of Sustainable Marine Energy, another tidal stream startup based in Scotland. His vision has been influenced by seabed-mounted turbines he's worked with before.
We were installing a first-generation device on the seabed. And so we looked at that and we said, that's great, we can see the potential for this, but it has to be far simpler and far more cost-effective. And that's when I decided to look at other ideas, and that's why we started Sustainable Marine.
In 2017, Jason's team assembled a new device to harness the power of tidal flows at the Falls of Laura. But he decided to try a different approach. His plan was to build and test a floating platform with tidal turbines that can be lowered beneath it.
We thought by having a floating platform, then we can make it more like a conventional ship. And we can take a little boat and we can go there whenever we want. And if we need to change a fuse, if we need to try a new blade, if we need to try anything new, we can do it, and it's easy.
The platform is held in place by mooring lines, while 4 relatively small rotors are lowered down into the water. As the tidal stream flows past, the turbines generate 280 kilowatts of power. When the tide turns, the platform is carried around by the current, so it can produce electricity on the rising and falling tides.
We are producing electric current with the turbines submerged under the water, and this is then transferred to the container for power conversion and then be fed into the grid. This is the next generation of tidal power.
Unlike seabed-mounted turbines, floating platforms are not hidden from view beneath the waves, so they do have an impact on the landscape. But being at the surface does have other benefits.
The water flows faster at the surface because at the bottom of the ocean you have the seabed, and the water moving along next to the seabed encounters friction. It has to get past all the crevices and rocks and everything. Therefore, you want the turbines positioned as high in the water column as you can get them to get the maximum amount of energy out of the water column.
With a faster flow of water, even small rotors can generate powerful forces. So the team need to check whether the mooring lines can hold firm.
The thrust force that's generated by one of our turbines is the same as a Eurofighter Typhoon when it's on full afterburner. So if you imagine with our platform, that's like saying, let's take a brace of Eurofighters and try and put them on a leash and then hit the afterburners. So that's how big the challenge is.
The trial in Scotland has proved that the mooring lines and platform can withstand the colossal forces and generate electricity reliably. But to be used more widely, the team also need to check how their technology affects wildlife.
It's all very well going and deploying something into the natural environment and saying, hey, this is going to help us avoid greenhouse gas emissions. But what impact is it going to have on the local environment? And we need to understand that to ensure that we don't create a situation where we create unintended consequences.
Researchers are monitoring the behavior of marine animals around the platform and investigating what effect the turbines could have.
Tidal turbines are mechanical structures. They make noise. There's often concerns about the amount of noise they make, that it's too much, that it pollutes the environment. However, we've got other concerns about tidal turbines, that they might be a risk for marine mammals and other large animals swimming around in the water column, and the risk is that they might bump into the turbines. So it's important that the noise that the turbines are making is loud enough for the animals to hear it at a distance that's far enough away for them to move away, but not so far that they avoid the whole area where the turbines are and the environment they're going through. So there's a kind of sweet spot between being too loud and causing disturbance and being too quiet and them having a collision risk.
So we've had seals and porpoises and even whales come past the platform, and we've had no signs of any interaction, and they just seem to cruise on by. The seals actually seem to like to play behind the platform somewhat in the wake. And now what we're really trying to understand is how fish interact around the platform and how they avoid the turbines.
After successful test campaigns, the team intended to scale up the device. As head of research and development, Penny Jeffcoat worked with the engineering team to create the new blueprint.
One of the things that we learned from having a 4-turbine platform was that the platform and the mooring system cope perfectly fine with all of the thrust and other loads that we were putting through the system. So it meant that we felt confident that we could design something that could accommodate more turbines and more power and more thrust and more load.
Before building the new larger platform at full scale, they had to be sure the design could withstand the extreme conditions it would face. The Flowwave testing tank in Edinburgh, Scotland is the only place in the world that can reproduce any sea state. With a circular shape, it can create every possible combination of waves, currents, and depth.
This means that we can completely accurately replicate what we would have in the real site, but at tank conditions. So it means that we can have flow coming in one direction, waves coming in another direction, and test this at different depths to see how these different phenomena interact.
In 2018, Penny's team built a scale model of the new design. The 6-rotor platform is destined for the Bay of Fundy in Canada, a location with notorious conditions.
It has the highest tidal range in the world, so you've got a 16-metre tidal range. So the flow speeds that we experience at site are between 5 and 6 metres per second. So for the mariners out there, that's more like 10 to 12 knots. So incredibly fast moving water.
As well as dealing with the rapid flow and constantly changing water depth, the platform must be ready for the worst weather that nature could throw at it.
We try and capture as many different combined conditions between flow and waves that we can do, and this might be quite benign. And then we also try to do right up to the extremes. So imagining a big storm coming through, a big hurricane coming through, massive waves coming through the site, how does the platform cope when it's confronted with these monster waves coming through?
As the tank test began, the paddles created miniature versions of storm waves. Underwater, pumps began driving the flow rapidly across the tank.
There is a certain feeling when you're in the tank and you hear all of the pumps like ramping up. And it's brilliant because it just builds up that sense of excitement and anticipation in you. When we're trying to replicate the Bay of Fundy, where we have these really extreme tides, it's actually pushing the tank right up to the extremes of what it can cope with as well.
But as the pumps reached full speed, something was not right.
Sometimes things don't go quite as you're expecting, and this happened quite unexpectedly, that we had a mooring line suddenly break on us as we were operating at the fastest flow.
The team rushed to find out what went wrong, and the answer was soon clear.
It was not through engineering or design, it was completely through me putting the models together slightly wrong, so I apologise for that to the team. But it was a really interesting thing to learn from because we saw exactly, well, what happened to the platform? Where did it go? How did it move in the tank? And actually, even though we lost one mooring line, the platform worked perfectly fine, it coped.
Once the mooring line was fixed, the waves and currents were ramped up again. And this time, everything went to plan.
We were throwing the fastest flow, the highest waves, and it was just performing exactly as we expected. So it was a real sense of such relief and excitement and just real proud of our engineering team for having designed such a brilliant product that did exactly what we were expecting it to do and did exactly how the numerical models predicted. And we had great confidence that yes, we can build this, we can put it in the sea, and it's going to do exactly what we need it to do.
On the east coast of Canada, the Bay of Fundy in Nova Scotia is the ultimate tidal testing ground. The full-size platform is being assembled on the banks. On the 1st of February 2021, it's finally ready to be launched. All they need now is for the tide to come in and raise the water level high enough.
Behind me you can see Plate Ice 640, our tidal platform. And in a few hours it's going to be traveling down this slip. It'll achieve high tide in about 1 o'clock today. We have beautiful wind conditions today, very low wind. So very, very exciting day. This is a culmination of many years of research and development, and can't wait to see our platform in the water.
At high tide, the platform is maneuvered down the slipway and into the bay. It will be moored in a passage with one of the fastest flowing tidal streams in the world. At full flood, 4 times more water moves through the Bay of Fundy than all the world's rivers combined.
Because it's so much energy, it's a very, very challenging site. It's the Mount Everest of tidal sites. And there have been some attempts to deploy technology there before, but unfortunately, nothing's actually managed to work for a prolonged period of time.
If it survives the ultimate test, this still relatively small platform could one day provide electricity to remote islands and coastal communities. But another company back in Scotland think bigger is better. At a construction yard in Dundee, the world's biggest tidal turbine is taking shape. The orbital O2. Making larger turbines means you need fewer of them to generate the same amount of power. That means fewer cables, anchors, and mooring lines. And less infrastructure means cheaper electricity. But CEO Andrew Scott knows that building bigger also has its challenges.
So this is the O2 superstructure. We've got a hull length here of just over 72 meters, which is actually about the same size as a 747 jumbo jet. The reason that we need such a big hull is that we're generating a lot of power. So we need to actually have buoyancy to counteract the load that is coming from the rotors. So each rotor is imparting about the same thrust as a jumbo jet's engines taking off.
Each of 2 rotors on the O2 will be 65 feet across. Together, they trace out a total area bigger than a basketball court. As the rotors turn, as well as generating electricity, they'll create a powerful torque pushing the front of the machine underwater. The buoyancy of a long tube full of air counteracts the turning force, keeping the nose above water. But in doing so, it causes the structure to flex in the middle.
The rotors exert tremendous forces on the hull, and the hull has to react all this force, and during this process, the hull bends like a banana.
Engineer William Annell has responsibility for the turbine's superstructure. He knows they need to reduce the bending motion as much as possible.
So you can see here that we have to use very large pins, really thick bits of steel in order to resist the forces that are being exerted on the structure. Now, the reason that we do this is to bring the stress levels right down. Some of the bits of plate that we have here are around about 70 millimeters thick. Even the hull has shell thickness of up to 40 millimeters thick in places. Now, if you compare this to a commercial vessel or a military vessel like an aircraft carrier, you'll find shell thicknesses around 8 millimeters.
When the hull was being fabricated, shaping and welding such thick pieces of metal into precise tubes was extremely demanding.
The hull structure has to be manufactured with a lot of precision. In order to resist the forces of the tide, it has to have good uniform shape. The tolerances that we're working to are around about 2 millimeters over 3.8 meters. So that's really high precision stuff. This takes a lot of experience because there's so many factors involved. It's a bit of a dark art.
The design of the O2 owes much to Orbital's previous turbine, the SR2000.
The SR2000 was a tremendous machine. It was a 2 megawatt tidal turbine, 2 rotors extracting energy from the tide, weighed about 505 tons. It was absolutely enormous.
Like the O2, it has a long superstructure with 2 legs to hold the nacelles and rotors underwater. In 2016, the SR2000 was unveiled at the Harland and Wolff shipyard in Belfast, Northern Ireland. Before launch, the team ceremonially blessed the vessel with mugs of local scotch.
There was a lot more effort making the SR2000 than what we'd anticipated. A lot of 12, 15-hour days. So it took a lot out of us. And for me personally, when the machine was launched, there was a sense of relief, and then there was a quiet sense of satisfaction for everything that we'd achieved. When it was launched, it was the largest tidal turbine in the world.
The floating SR2000 was towed north to Orkney, where it was moored in one of the world's fastest flowing tidal streams. Over the course of a 2-year-long trial, the turbine survived waves over 4 meters high and broke the record for the most tidal energy generated by a single turbine, 3 gigawatt hours in its first year alone. This provided the 20,000 inhabitants of the islands with up to a quarter of their electricity.
We made a lot of world records. We made a lot of world firsts as well. We had a very successful testing period generating significant amounts of energy from a tidal turbine, and that hadn't been done before.
But although the SR2000 performed well, the team soon became aware of a major drawback. The 2 legs holding the rotors were designed to tuck up underneath the body, making it easier to tow to harbor. But that meant the rotors and nacelles would always be below the surface, and therefore hard to reach.
It was flawed. By having the nacelles always under the water for the SR2000 meant that inevitably, either through needing to access for servicing or repair, we were going to be faced with the question of having to get access. And that would have to be done either by lifting the entire turbine out of the water or put it into a dry dock. Both those scenarios require a lot of downtime and a lot of cost.
The team couldn't afford to take that risk again. Even something like a blown fuse could take the turbine out of action for weeks. Andrew was determined to find a way to make all the vital components on their next turbine more accessible.
We knew that we had a challenge around low-cost maintenance and servicing of the entire turbine, including the nacelles. So that was something that we put as a priority for the redesign of the O2.
One approach would be to change the position of the legs so the blades and the nacelles could be lifted all the way to the surface rather than being tucked up underneath the hull. But that would mean the turbine could no longer be put in a compact configuration that could easily be towed and docked. Then Andrew realized that if the nacelles and rotors were accessible in situ, that wouldn't matter, as it would never need to be taken to harbor for repairs.
It gave us a bit of an hallelujah moment in terms of how we operate these turbines. And what that really allows us to do is make sure that the turbine spends most of its life generating power, which is what it's meant to do.
In July 2020, the mechanism for the O2 legs was tested for the first time. Lifting them right up to the surface requires new, more powerful hydraulics. The untested technology must now prove that it works.
Today we're just testing the hydraulic retraction system. It's a huge amount of weight, 100+ tons that it has to lift up to the surface. So it takes a huge amount of power to do that, 75 kilowatts of hydraulic power just to lift the legs.
The upper parts of the legs have been attached to the body, ready to test the mechanism. All that's left is to lower them down to their working position and then try to lift them back up.
We don't like excitement. We tend to want the testing to be well planned. I like a boring test. Okay, I'm going to take the legs down.
The legs are fully deployed with no surprises. Next comes the 100-ton lift. On the water, this will raise all the vital components up to the surface, where they can be easily accessed. success. By January 2021, the nacelles are ready to be attached to the legs. Inside are many of the vital mechanical components, including the gearbox, generator, and pitch control units. The final components are the rotors. Although tidal blades operate along the same principles as those on wind turbines, working underwater makes a huge difference.
As a comparison, this wind turbine has a power output of about 11 kilowatts and blade length of about 6 meters. So to do the same with the tidal flow, we'd only need blades of about half a meter in length. The difference is due to the density of water. Seawater is more than 800 times denser than air. The energy density in the tidal stream allows us to generate a lot more power for a given swept area.
Finley Wallace is the lead blade designer at Orbital. The blades he's creating for the O2 will be roughly twice the length of this small wind turbines, but should capture 100 times more power. The rotors are being made in Gosport, England. The team are using layers of carbon fiber, a material that once treated will have the right strength and stiffness to reinforce the structural core of the blades.
The forces involved in acting on a tidal blade are orders of magnitude higher than an equivalent wind turbine blade. So standing up to the marine environment is the real difference for me.
To form the core of the blades, the carbon fiber must be infused with resin and then heated.
We're actually standing inside an oven at the moment, looking at the main structure of the O2 2000 blades. There'll be 4 of these produced, 2 for each rotor set, and they'll do the majority of the work of transmitting the blade loads from the tidal flow into the turbine structure.
While the core of the blade should be strong, the exterior must be perfectly shaped to interact with water and generate power.
I spent a lot of time fine-tuning the external shape of the blade to present the smoothest path for the water to flow over. The water flowing past the blades is what allows us to generate electricity from the water itself.
The computer-controlled cutter can exactly recreate the hydrodynamic curves of Finley's digital design. But the automated process leaves unwanted ridges on the surface. These are smoothed out by hand to produce a perfectly polished edge.
Being able to kind of stand in front of the molds and see that it's kind of gone to plan, as far as that's concerned, has been very rewarding.
In February 2021, the blades arrive in Dundee, ready to be painted and attached. Once in place, Orbital will test the giant turbine back in Orkney. When they connect to the grid, it should generate more power than any other tidal stream turbine. After that, they have big plans.
The long-term goal is to produce lots of machines so that we can have farms of tidal turbines in various sites around the UK and around the world.
In the future, arrays of tidal stream turbines could generate huge amounts of power for local communities and national grids. Yet despite the clear promise of the technology, some experts question whether tidal stream power could ever become as widespread as wind or solar. Surveys suggest the number of places with fast enough currents is limited. In the vast majority of coastal locations, the water simply doesn't flow fast enough for seabed-mounted or floating turbines. However, a company on the west coast of Sweden is trying an approach that could work in more places, with a design that's fundamentally different from other tidal stream turbines. Rather than being fixed in place, this turbine is designed to move. CEO Martin Edlund believes this is the secret to extracting more power from slower currents.
The Minesto technology is unique compared to hundreds of other tidal solutions that exist today. So what we do is that we basically fly an airplane underwater tethered to the seabed. This technology can be used in all continents and all oceans around the globe, and that's a huge advantage.
The Deep Green 100 prototype has wings like a plane, but it moves more like an underwater kite. On a day with slow winds, there's a trick that allows you to still fly a kite.
The wind speeds today is really near to nothing, about 1-2 meters per second. But flying the kite in a figure eight allows us to get more energy out of it.
When there's not much wind, a stationary kite can't stay aloft as there's not enough power in the air to lift it. The only way to fly a kite in these conditions is to keep it constantly moving, faster than the wind itself. That way, it collects and combines the power of the wind over a much larger area, keeping it in the air.
Our turbine is like a normal kite, but instead of powered by wind, it's powered by water. That's exactly how a kite behaves underwater, in this figure eight behavior.
Monesto's subsea kite is designed to be tethered to the sea floor and to move continuously through the water in a figure of eight, flying much faster than the water is flowing itself. The rotor on the front is pushed round, generating electricity, which flows down the tether and back to shore. By harvesting the power of the flowing water over a large area, it can extract many times more power than if it were fixed in place, like other turbines. At the workshop, the gearbox, generator, and the rudder module are being tested. The team are checking that the systems are correctly calibrated so it can maneuver reliably underwater.
We're doing some fine-tuning of the most important section of the kite that actually doing the work, which is the rudder module, rudder and elevator module. So we have the rudder here that controls the steering of the kite, and then we have the elevators, which is basically the throttle.
The rudder module is entirely responsible for the kite's trajectory underwater. If it doesn't move as intended, the kite could crash into the seafloor or tie itself up in knots.
Maybe 1 degree of difference has a huge impact on the performance of the system. So we really need to nail this so we get the most out of the system.
The rudder and elevators are connected to an onboard control module. Once the team have chosen how they want the kite to behave, it flies automatically.
It's what we call the kite control module. That's where the magic happens. We create system code, clearly, and then we program it into this control unit. And then we just tell the kite to run. And it will then automatically adjust its actuators within given parameters that we've set. It could be kite speed, depth, and so forth. And within those boundaries, the kite's making its own decisions and is really good at it.
To make the right decisions, the kite has a gyro unit and sensors. These tell the control module what depth, speed, and orientation it has at all times, so that it can respond appropriately. The team need to check all the sensors are working as intended.
If you imagine you have your smartphone, where you can flip the screen and you can like roll balls in games and those kind of, it's more or less the same thing. We set the kite into motion and we can see that the rudder module reacts the way we want it to. So we're happy.
Monesto have been testing underwater kites for 10 years around the coasts of Northern Ireland and Wales. During that time, they've developed their seabed tethering technology and devised the most efficient systems for transporting the power back to shore. All this while improving the technology that flies their kites through the water, leading to the development of the high-performance DG100.
We needed the robust systems to fine-tune and work with control system, get all the functionality in place. But what we're doing now is that we're aiming higher and we're moving towards real performance output of what we're doing. And I think it's fair to say that this version we have now is more of a Formula One car than a robust, safe Volvo that we've been working with before.
Monesto chose the Faroe Islands in the North Atlantic to trial the DG100. Here, the tidal currents are much slower than in Orkney or Canada. But Monesto calculated they could still supply 100 kilowatts of electricity to the grid, enough to continuously power over 1,000 TVs.
The flows in most locations are not high enough for what we may label conventional tidal turbines. For us, this campaign is the key campaign to really prove the high-performing energy conversion that we're claiming, which makes it then sort of the absolute most important testing campaign that we've had in Monesto.
First, the team had to build the infrastructure to fix the kite to the seafloor and bring the power onshore. Once that was in place, the kite was towed out to sea. But during tow testing, the team realized that there was a problem with the electrical connection. The system had detected a leak, which had to be fixed.
You can imagine, I mean, we're all excited about this control system team in place. Everyone really wants to see this thing flying. And then there is a minor, insignificant part of a component that sets us back again in this. That's sort of the nature of pushing the boundaries of technology and driving innovation.
After 3 weeks and a lot of late nights, the kite was back in the water.
Towards the end of November, we had really good tidal conditions, good weather conditions, and we said that it's about time now to get everything right and hook this machine up to the grid and fly it. And we knew that we were very, very close to success.
The tether was attached to the seafloor. And in the control room, everything was finally ready. The team were raring to go. The kite sank deep into the murky depths and out of sight. Finally, the test could begin.
We started running it in continuous operations mode with some safety belts on, not letting it loose completely.
The target was 100 kilowatts of power.
66.5 kilowatts. We knew that the tidal conditions were really good, so it was tempting also to have a go at really optimizing and driving the electricity production to the peak levels of the system. So we actually run the system beyond the 100 kilowatts it's rated for.
To everyone's excitement, the kite reached 101 kilowatts. Then continued rising up to 117.
The atmosphere in the control room went from a really tense and concentrated environment into really relief and joy and people being really, really happy and proud about what we've achieved.
Monesto's prototype only generates a fraction of what larger turbines can produce. But they plan to build a machine 10 times more powerful, which would thrust them into the big league.
Around the world, there are thousands of potential installation sites. All continents and all oceans have an abundance of kinetic energy of the kind that we can use. And we talk about a capacity long-term that will be in the range of what nuclear is providing to Earth today. So it's not just sort of a niche technology in that sense. It's something that will play a global role in contributing to getting us where we need to be as humans.
If Monesto successfully scale up their kites, this technology could hold huge potential for the future. In the meantime, others are rapidly proving that tidal stream energy could make a big splash even sooner, with full-scale turbines ready to go. Atlantis have started deploying their turbines around the world.
We are busily planning our first project in France. We've just sent a turbine to Japan. It's the first of its kind in Japan, and we also designed and helped install the first 500 kilowatt turbine in China earlier this year. You've got so much potential around the world for the deployment of this, we're never going to be short of customers.
Sustainable Marine are busy conquering the Bay of Fundy in Canada. if their platform works there, it'll work anywhere.
I think where our technology can really make a difference is in these remote island and coastal communities where perhaps they don't have the best solar resource, perhaps they don't have the best wind resource, but we can give them a renewable and predictable source of power.
And Orbital are putting finishing touches to the biggest and most powerful tidal stream turbine the world has ever seen.
The challenge of climate change, it doesn't need just one solution. It needs lots and lots of different solutions. So we really want to exploit this pioneering, enabling bit of technology that we've developed here to see it used as widely as possible around the world to generate clean, sustainable power.
A new golden age of ocean power could be around the corner.
100 years or so ago, tidal energy was really pushed out by fossil fuels because they were cheaper. But we've now seen the problems we're having with fossil fuels and the impact it's having on the planet. So I really see that tidal energy is on its way back. And frankly, I think tidal energy is going to get its revenge for being pushed out.
When it comes to energy, could the tide finally be turning? We face one of the greatest challenges in the history of humanity. To eliminate the fuels that have driven progress and technology for over a century. While our thirst for energy only grows. Could the solution lie with an ancient and distant power source?
It's without question that in our solar system, the sun is the greatest source of energy. And the better we can take advantage of that, the better it is for us as a civilization.
It's like a nuclear reactor in the sky, and it provides endless power. And if we can harvest just fractions of this, it can power all our consumption.
Giant strides have been made in capturing the sun's energy. But to replace fossil fuels, solar power needs to step up a gear.
We've got a long way to go. The way I see it, we've only got 2% of the world's energy is solar. So there's a massive opportunity there, and this technology is made for it.
Engineers are racing to capture more of the sun's power, to open vast new expanses for solar panels, and even to make solar electricity available through the night.
This is the full cycle that allows us to keep generation 24 hours using 100% only renewable energy, the light from the sun. This is the future.
The vast majority of solar power today is generated by silicon solar panels. These are made of many individual cells. Each cell has two thin layers of crystalline silicon, which have been altered so that one is slightly negatively charged while the other is positive. The magic happens when light falls on it. Electrons in the silicon atoms absorb the energy and break free. The negatively charged electrons are then drawn towards the positive layer. Once connected to a circuit, this flow of electrons becomes electricity. Solar panels like this are on rooftops all over the world, producing clean, green electricity to power our homes and charge our gadgets. But transportation is a much tougher challenge. It's still overwhelmingly powered by fossil fuels. A tech startup in Holland has gone right back to the drawing board, inventing a new car from first principles that could revolutionize personal travel. Their goal is to prevent billions of people buying gas-powered cars by offering them a vehicle that charges itself for free.
Everybody said we couldn't do it, and that's what makes it interesting.
So I think that's actually one of the things that motivates us, that it seems like an impossible challenge. And actually, if we look back at the beginning, it all started with the World Solar Challenge.
Their story began at a race across Australia. Every 2 years, a fleet of futuristic vehicles can be seen streaking across the desert. This 1,800-mile race is powered by the sun, with cars built by students from around the world. In 2012, a Dutch team from Eindhoven, including electrical engineering student Arjo van der Ham, decided to enter for the first time.
I think most people were there for the adventure and for actually building something with your own hands during your studies and seeing it work and then trying to win the race in Australia.
In previous years, all entries had been one-seaters, built purely for speed. But that year, the team decided to enter a new category that awarded extra points for comfort and practicality. The idea was to encourage the development of a commercially viable solar-powered car.
We said, okay, let's build a four-seater car. And that became Stella, the world's first solar-powered family car. It was a car that had a flat roof, especially because of the efficiency of the solar panels. Furthermore, it was very aerodynamic, it was very lightweight. It was made almost completely out of carbon fiber.
The team had just over a year to fully design and build a radical new solar car that could also be a practical family vehicle for everyday use. Stella, they hoped, would be the blueprint for the car of the future.
People would be sleeping actually at the university, waking up, build a solar car, go back to sleep for 6 hours, wake up and go build again. So this was really an intense period for most of the people in the team.
On the 6th of October 2013, the only family-sized car in the race crossed the starting line in Darwin, Australia. For the next 6 days, Stella would be racing through the desert, powered by the sun, albeit accompanied by gas-powered support vehicles.
During the race we had the solar car, and then in front of that we had a small van called the strategy van, and was packed with computers, and we had 2 guys, so me and my buddy, modeling and calculating exactly how fast should we drive with the solar car such that at the end of the day our battery is exactly empty.
Everyone expected the comfortable 4-seater to be much slower than the others. But by day 3, she'd hit 75 miles per hour. So fast, the team bus couldn't keep up.
Kijk in de spiegeltjes, zie je het stipje steeds groter worden natuurlijk. Een apart moment als je ingehaald wordt in je eigen zonneauto. Dat was een goed momentje. Ja.
Before long, she'd overtaken their leading competitor, Team Bochum from Germany, despite carrying twice as many people.
Komt die reactie? Oh shit. Ja. Hallo, goed bezig, joh.
But the following day, the car ran into difficulty and needed an emergency pit stop. The team fixed the issues, but they'd lost precious minutes. And on day 5, they lost even more time to their rivals.
Ik heb even getimed ook. Het eerste uur lagen we al 10 minuten achter op Bochum.
By the morning of the final day, the race was still tight. But Arjo had a trick up his sleeve.
En zo laden we nog ongeveer 2 à 3% bij in de batterij. Waarmee we zo meteen weer net wat harder kunnen rijden. Dus qua tijd liggen ze redelijk voorop, maar als we naar de scores kijken, dan gaat het heel close worden tussen Bochum en ons.
Stella crossed the line in Adelaide having driven 1,900 miles in 40 hours, with an average speed of 47 miles per hour, the second fastest in the category. But the cars weren't only judged on speed. They could earn extra points for the number of passengers carried and how it would fare in the real world. And it's here that Stella came into her own.
a jury would take your car and see if they can parallel park it easy, how many suitcases would fit in, are there any cup holders, how easy is it to get in and get out, etc. And they would score points on that for all the different cars, and then all of these scores combined would make up the final winner of the cruiser class.
With bonus points for real-world credentials, the team squeezed ahead of the competition and took first place with a family-sized car. But they knew that to really make a difference, the hard part was still ahead of them.
But at that point, you're not really changing anything, right? You're just making one car and driving it through the desert of Australia, and there's 5 trucks behind it to carry all the spare parts. So you really have to take the concept to the market to really make an impact and try and improve the planet in that sense.
Ayo and 4 other team members decided to make the dream a reality and launched Lightyear to make solar-powered cars for the public.
In 1 year, the entire fleet of cars throughout the world, they will drive 1 light year worth of kilometers. And the mission of the company is to get that to 1 light year of sustainable kilometers by 2035.
To achieve their mission, they set about turning Stella's outlandish design into something more attractive to consumers, while still keeping the radical approach.
We came up with our own scoring formula, what would make this car better. And the key metric that we optimized the Lightyear 1 for is the amount of miles you can drive each year on the sun. So the amount of miles you can drive for free. And that also guided all the decisions. So if you have to decide whether the car should be a bit wider to accommodate more solar panels or whether it should be a bit smaller to make it more aerodynamic, you calculate how much solar kilometers would option 1 give and how many solar kilometers would option 2 give, and then make your decision. So this is what guided the development of the Lightyear 1.
As Chief Technical Officer, Ayo has overseen the design of the solar panels. At their workshop in the Netherlands, Lightyear are fixing them in place. With panels on the roof and the bonnet, they cover 54 square feet in total. But although they work in the same way as a standard panel, Ayo has altered the structure to maximize the power. A special technique can reveal the design.
We can actually show the structure of the panels and any defects that the panel will have using an EL test. And with an EL test, you actually use the solar panel in reverse. So normally the solar panel would turn sunlight into electricity, but if you actually do it the other way around and you provide the electricity to the panel, it will work as a light source. And it will light up in the infrared spectrum. And now we make it dark in the room, so we turn off the lights. We take a picture with the camera that's modified to actually show up the IR light, and then we can see the groups lighting up. You see all of the cells lighting up, but there's a couple of exceptions. So this is actually an old panel that we used already for a lot of tests and we abused quite a bit. So that's also the places where the solar cells themselves don't work anymore.
Like an X-ray, as well as showing what's broken, the image reveals the inner structure.
So to increase the power output of the solar panel, we've done lots of small tricks, like putting all the solar cells pretty close to the edge. We've cut them to a smaller size, and that way we can place them closer together.
Lightyear claim these are the most efficient solar panels on any car, with the improvements gaining them 20% more power. And as well as squeezing more solar cells into every square foot, Ayo has divided them into groups. To see the benefit of that, you need sunlight. Luckily for countries like Holland, the panels even work on a cloudy day. First, Ayo is connecting this regular solar panel to a voltmeter. This will reveal what impact shadows can have on the power they produce.
So we've connected the panel to the meter, and if I put a shadow on it, you will see this number dropping, and it actually doesn't matter where I put the shadow, you lose the same amount of energy.
If a shadow falls on even one solar cell, the power generated by every other cell drops by the same amount, even if they're in sunlight, because they're all connected. So the whole panel becomes much less efficient. This doesn't matter much for panels on rooftops that rarely have shadows fall on them. But cars regularly drive under trees or past buildings.
On this panel, we've actually divided the panel into 11 very small panels. These 11 very small panels allow us that if one of them is in the shade, one cell, it will only shut down one small group of the panel and not the entire panel. And we can actually demonstrate this. And if I go over it with this board, then I create a shadow on the front, and then only the first meter will show that it actually drops, and the other meters, they still show the same value. And then if I move it along, the value on the first meter actually comes back, and it drops on the second meter. And then if I move even further along, the same thing happens on the third meter. So as I go over the different groups, I will only shut down the performance of that group and not of the entire roof, which you would see on a regular panel.
As if reinventing the solar panel wasn't enough, the Lightyear team have an even bigger engineering goal: making the car one of the most efficient ever produced.
The Lightyear 1 is designed to maximize the amount of miles you can drive each year on the sun. And if you break that down, then the biggest factor is aerodynamics. So making the car more aerodynamic is where you can save the most on the energy consumption of the car.
Most of the design process happens using computer simulations. But now the team must prove how streamlined the car really is. Annemiek Koers is responsible for Lightyear 1's aerodynamics.
We are currently in the wind tunnel with the prototype of Lightyear 1 to test how it performs at different speeds. So we test the airflow over the car, how much drag does it produce, and what effect that has on the range eventually of the car.
The tests will reveal the drag coefficient, a number that tells you how much wind resistance the car has. The target is to get down to about 0.2, which would equal the most streamlined production car ever made. With such low drag, it could drive much further with the precious solar energy it collects. But compared to a regular car, the team face an extra challenge. As well as being streamlined, the shape must also fit enough panels.
The aerodynamics are a bit constrained by the solar roof. It needs to be quite flat surface on top instead of having very curved surfaces, which would be maybe better for aerodynamics.
But the team have managed to find a profile that boosts both the solar power and efficiency. One that gives a larger area for the panels while also reducing drag.
You can see that we have a very shallow slope going to the rear, and the flow can stay attached over that full length. And if you have a shorter car, we will have a steeper slope, and that will detach the flow and will create a lot of drag.
The team analyzed and modified every inch of the car, replacing bulky wing mirrors with streamlined cameras and fixing covers over the back wheels. Eventually, the team get the drag coefficient down even further than they'd hoped, below 0.2.
So we can claim to be the most efficient production car by the time we get to production, but that's of course the first step.
This world-beating efficiency means the solar energy can go much further, even in cool, cloudy countries.
The solar panel will actually give you enough energy to drive somewhere around 8,000 kilometers per year in the Netherlands. It doesn't sound like that much, right? 8,000 kilometers. But the average car in the Netherlands actually drives only 11,000. For California, they drive much more, but there's also much more sunlight, so you get again around 70% of your annual energy need you get from the solar panel.
For the other 30%, the Lightyear 1 can be plugged in and charged like a regular electric car. For now, to pre-order one will set you back well over $100,000. But it could also save thousands at the pump.
Towards the future, we will be developing an affordable version of the Lightyear 1, and we see energy efficiency as the key to the price in the longer term.
But while solar cars may still have a premium price tag, the cost of standard solar panels has already plummeted. The main mineral used to make solar panels, quartz, is abundant and cheap. And by mass manufacturing in large factories with automated production lines, they also cost less to make.
Solar power now is the most affordable source of power. It's just a matter of capturing this energy. And solar power now beats coal-fired power, diesel generators. And now hundreds of millions of the solar panels are manufactured every year.
With such cheap panels available, solar farms have mushroomed. Many are so large, they're visible from space. Some generate over 2 gigawatts of electricity, enough to charge 400 million phones at the same time. And yet solar power still produces only 2% of the world's electricity. That's because although panels are cheap, they need the right kind of location.
So one of the challenges, and this is now starting to happen with the very high number of solar panels, we are searching for new places to put them. And it's a quest to find these areas in good positions.
As solar farms get bigger, they start to compete with other uses for the land, such as recreation, farming, forests, and other wildlife habitats.
It's questionable whether to set aside big surfaces for the solar farms. And it's becoming more and more difficult to find good spots for at least very large solar plants.
To solve this conundrum, an entirely different approach is starting to make waves. Børge Bjørneklært is the founder of Ocean Sun, a company making platforms for solar panels that float. Børge realized that there are water bodies all over the world with readily available sunlit surfaces. Many, like the Magat Reservoir in the Philippines, are next to hydropower dams, which has a big benefit.
One very nice thing about combining floating solar power and the hydroelectric power is the very short distance from producing solar power to delivering it out to the grid, because the infrastructure is already in place at the power station.
The solar panels generate electricity when it's sunny, while the dam makes power when it rains.
It has the flexibility over the seasons. For the rainy season and the dry seasons, you can make a more steady power production. So this combination is a fantastic application.
Other companies are also targeting lakes and reservoirs. But Børge has set his sights on a much bigger body of water, the sea. The main obstacle is the ocean waves.
The challenge is very much to create a protective environment for the solar panels, and also to cope with waves and also strong winds that can occur on water surfaces.
Ocean Sun tested their design off Norway's coast. The most critical piece of engineering that protects the panels is also the simplest: the thin polyethylene membrane that forms the surface.
This is the fabric of our system, which we place the solar panels on top. As you can see, it's less than 1 millimeter thick.
It interacts with the surface tension of the water to create two curious and powerful effects. Firstly, it boosts the strength of the material.
This fantastic effect that this layer has when we put it on top, and it came to us as a big surprise that you could actually walk around on the water surface through this very thin fabric.
And secondly, Børge discovered that the membrane changes how water behaves.
It has a dampening effect on the motion of the waves, and it serves as an ideal surface for placing solar power on top of it.
In January 2019, the floating system had a chance to prove itself.
In the winter, we had a pretty bad storm coming in over Norway. Bridges were closed and the ferries stopped, and we really got to test our system in quite bad conditions.
The floating solar array was hit by high winds and waves. Once the storm had blown over, the panels emerged unscathed and still generating power. Having proved it can survive harsh ocean conditions, sea-based solar seems perfectly placed for an energy revolution, as nearly half the world's population lives near the coast.
Many big cities, like here in Oslo, have the ocean right on their doorstep. And if we can use the surfaces here for floating solar power, you have a very short transmission to the consumers.
Research is underway to minimize any negative impact on marine life. So far, results have shown that floating panels appear to reduce damaging algae blooms. With water surfaces now available as well as land, experts estimate that 70,000 new solar panels are being laid every hour, equivalent to 1,000 soccer fields a day. But although solar is already the world's fastest growing energy technology, it could be generating even more power. Standard solar cells can only convert about 1/5 of the energy that's available in sunlight into electricity.
The fundamental problem with your standard solar panel is it captures the little bit for electricity, 15 to 20%, and throws the rest away.
If that percentage were increased, we could accelerate the transition to clean energy sources. In Victoria, Australia, a company called Raygen think they have found a way to harness more of the sun's power. Inventor John Lassick came up with part of the solution as a student way back in 1975.
I was pretty ambitious for a young lad, and I thought if you're going to make perhaps a quarter or even half of the world's energy from solar energy, you have to have something that is highly efficient and very, very powerful.
In the 1970s, solar panels were small and even less efficient than they are today. But John had a simple idea how to supercharge them. He calculated that a parabolic dish with a reflective surface could focus sunlight onto one small solar cell, concentrating the power of the sun like a magnifying glass. So he had a parabola-shaped bowl made for him in pottery class and then ingeniously lined it with a reflective bag from a box of wine.
I put those two items together and produced a solar concentrator. We produced several hundred times more power out of that cell. And at that moment, I knew we're onto something.
Briefly, it seemed John had found the perfect way to capture the sun's energy. But he'd overlooked one thing.
Unfortunately, about 10 seconds later, the cell fell to pieces because of the very high intensity and the heat that reached several hundred degrees.
To overcome this, John developed a way to protect the cells from overheating, a system he still uses today.
Normally, we'd expose these to 750 suns of intensity, and what we have to do is have a module that is that tough it can stand a blowtorch. It's the equivalent of 750 suns of intensity.
The apparatus keeps the solar module cool even when blasted with heat intense enough to melt steel. The secret system involves pumping high-pressure water through the back of the panel.
Stone cold. That shows how effective the cooling is, and it's stone cold.
With the heat problem solved, John scaled up his idea into bigger and bigger dishes. Eventually, he found a system that could focus even more sunlight. At RayGen's pilot plant in Bendigo, Victoria, instead of focusing sunlight with a parabolic dish, they used giant mirrors. These reflect sunlight onto solar modules at the top of 3 tall towers.
What we do is we put an array of these modules into a large receiver that has a field of mirrors that focus a massive beam of light to that receiver, where we can produce megawatts of electricity out of that array of modules.
The receivers are exposed to 750 times more sunlight than they would be on their own, and this allows another major technological advance. Their solar modules consist not of normal solar cells, which turn around 20% of sunlight into electricity, but of a special type called multi-junction cells, which produce far more power.
This is the flash test that we're about to demonstrate, and this measures the power and the performance of the module. So we take a module and we place it into the chamber. This machine simulates the sun. We have a flash gun at the top, which provides the highly intense light. We simply run the process, and the machine collects the vital information about the module. So the main indicators being the power at 2.27 kilowatts, the efficiency of an astonishing 36.9%.
Multi-junction cells can turn around 40% of the sun's energy to electricity, nearly double what conventional ones achieve. This is because sunshine consists of many different wavelengths or colors of light. Standard solar cells have one pair of silicon layers, which can only absorb a small range of those wavelengths. The rest is wasted. Multi-junction cells, on the other hand, have several pairs of layers, each made of different materials that can absorb different wavelengths. So more of the sun's power is harvested. Although multi-junction cells are around twice as efficient, their price is also higher. So they're normally only used to power specialist equipment like space satellites. But by concentrating the sunshine, RayGen only need a small number to capture a vast amount of light.
The trick that we have is, yes, we pay 100 times more per square centimetre for the cell, but we get 1,500 times more power out of the cell in our system.
When the sun is focused on them, just 2 of these can produce as much electricity as 20 full-size solar panels covering the roof of a large house. John has plans to scale up his pilot plant to produce gigawatts of power. And they can even share the land it's on with others.
All we can do is spread the collectors out a little bit, which makes the system very efficient, but it allows the grass to grow, and we can actually run stock at the same time. So you've got a solar farm and you've got an agricultural farm running on the same land. The beauty of a light footprint.
RayGen hope to disrupt the industry with their radical approach, harnessing even more of the plentiful power we receive from the sun. But despite its success, solar energy currently has a major drawback. Demand for power surges in the evening, just as the sun is setting. Unlike fossil fuel power stations, most solar farms can only produce electricity when the sun is shining. In the arid Atacama Desert in Chile, a major new development is aimed at solving the dilemma. Cerro de Minador. Like the RayGen plant in Australia, Cerro de Minador has a tower surrounded by mirrors that will track the sun and collect its energy. But the system works in a fundamentally different way and on a far bigger scale. Once complete, the tower will rise as high as a 70-story skyscraper. Francisco Vizcaíno is project director of this groundbreaking venture.
It is very important to develop projects like this, because if we really want to turn page on the fossil fuels, we need to create green energy, renewable energy that is able to work 24 hours in the night. When the electricity is really needed in the evening and you turn on your light, this is what we need.
Cerro de Minador is designed to produce solar electricity 24 hours a day, and more of it than anywhere else in the world. Northern Chile is the perfect place for this kind of solar installation, as the Atacama Desert is the driest place on Earth outside the poles. That causes the solar radiation here to be uniquely intense.
In Chile, the sun is much more powerful than any other place in the world, not only because of the power of the sun, which is strong, also because there is not water in the environment. It's very dry. So the light is coming directly to the ground without any reflection on the water in the environment. Even if the temperatures are not very high, the power that we are receiving from the sun is tremendous.
But there's a price to pay for choosing the sunniest spot on Earth. Firstly, it's also one of the windiest spots, meaning the mirrors need frequent cleaning from dust. And secondly, Chile sits in one of the planet's most seismically active zones and holds the record for the world's most powerful earthquake.
One of the most challenging things by constructing this kind of plants in the desert with this big tower is the earthquakes. The seismic movements, we need to control it by doing a special design and a special engineering and a special construction.
For the 820-foot high tower to be quake-proof, its foundations must be 24 feet deep. Once the main structure was complete, an enormous receiver was assembled for the top. This is where the sunlight will be reflected onto. But the 72-hour-long procedure to lift it into place had never been attempted before.
Lifting up this equipment was one of the biggest engineering and construction maneuvers in South America all time. It was one of the most tense moments in our life in construction. We have been lifting the receiver, taking care of the earthquakes and the wind, and it was a very, very difficult maneuver. By lifting 3,000 tons equipment from the ground 250 meters to the top of the tower was challenging, was difficult, but was very nice.
The receiver, which weighs as much as a Navy frigate, was lifted by 16 powerful hydraulic jacks. For safety, it had to be moved no faster than 16 feet per hour. After 3 days, the receiver reached the top and was successfully fixed in place. Once complete, the tower became the second tallest man-made structure in Chile and the 5th highest on the continent. As well as building the giant tower, the workers have a huge job assembling and calibrating over 10,000 giant mechanical mirrors called heliostats, spread over an area of 1,700 acres. Each one is the size of a helipad and can tilt in any direction. Today, the team in the control room are calibrating the heliostats.
Hoy día es un día muy importante porque nos encontramos ya prácticamente en la fase fuerte, la fase más activa de la puesta en marcha. Hoy día, cosas que pueden salir mal.
Jose Ramiro is the solar field commissioning manager. He must ensure that every heliostat can eventually reflect the sun's radiation accurately onto the receiver at the top of the tower. But as the sun moves through the sky, the heliostats must also move to keep the reflected sunbeam trained on exactly the right spot. If they're even a fraction of a degree out of position, the whole system could fail.
Aquí este sistema lo que nos da es la imagen del espejo concreto que estamos calibrando. En el día de hoy estamos controlando uno por uno.
For each heliostat to be able to automatically track the sun, the team must first train the reflected beam of light onto a target on the tower.
En estas imágenes tenemos las dianas que se encuentran en la parte superior de la torre, justo debajo del receptor. Nosotros procuramos siempre la mancha reflejada quede lo más centrada posible.
Once the light spot has been locked into position, the system will be able to find the black receiver automatically. One down, 10,599 to go. The best view of the heliostat field is from the top of the central tower. To get there takes a 13-minute ride in an elevator.
Here we are on the top of the tower, 220 meters, and here you see all the solar field with the 10,600 mirrors, which will be reflecting the light of the sun to the top of this tower, just where we are right now. It's very, very nice when in the morning they wake up and like sunflowers, they are following the sun and aiming the light of the sun to the top of the receiver.
From here, you can see the big difference between this site and conventional solar power plants. There are no solar panels anywhere. At Cerro de Minador, they will generate electricity a completely different way. A special liquid made from salt is pumped to the receiver at the top of the tower. Here, the reflected heat from the sun raises the liquid's temperature to a whopping 1,040 degrees Fahrenheit, as hot as lava. That molten salt is then pumped back down the tower, where it's used to heat water and make high-pressure steam. That steam drives the turbine and makes electricity. Cerro de Minador is not the first solar plant to generate electricity this way, but it aims to be one of the first to produce power reliably on demand 24 hours a day. Conventional batteries are much too expensive to use on this scale. So to generate electricity through the night, Cerro de Minador has two giant storage tanks at the bottom of the tower.
Here we have the tanks. The salt today is here, melted. 46,000 tons of salt inside those tanks waiting for being pumped to the top of the tower.
The salt from a nearby mine in northern Chile consists of sodium and potassium nitrates, which have the ideal properties to store heat safely and reliably. Once on site, the salt was melted. Then the liquid was stored in a tank. Despite being 600 degrees Fahrenheit, this is known as the cold tank.
In the morning, we have all the salt there in the cold tank. 46,000 tons of salt there. During the day, the salt is being pumped to the top of the receiver, to the top of the tower. In the receiver, we heat the salt, and we start to fill the hot tank. So during the day, the cold tank is getting empty, and the hot tank is getting full.
In the hot tank, the salt is stored at 1,040 degrees Fahrenheit. The tanks are so well insulated that the temperature only drops 1 degree per day.
During the full night, we are using that salt to generate steam, and at the end of the night, again, we have the cold tank completely full of salt, and this is the full battery cycle that allows us to keep generation 24 hours using 100% only renewable energy, the light from the sun.
Solar tower technology with molten salt tanks can generate solar electricity on demand 24/7. But they only work efficiently in countries with intense sunlight near the equator. If power from the sun is to truly replace fossil fuels, we need solar-generated electricity available day and night, everywhere. A team at the US Naval Research Laboratory is working on a way to supply solar power to any place, any time. It's called space solar, and it sounds like something from a science fiction movie.
The idea of space solar is that instead of collecting sunlight on the ground using a solar panel the way we usually do it, is we take that solar panel instead and put it in space and then send it to where you need it on Earth. We kind of take it for granted now that we can go anywhere on this planet and take out your phone and it tells you where you are. And we can do that because we have a system of satellites, the Global Positioning Satellites, which was also created here at the Naval Research Laboratory. And we're talking about doing the same thing for energy. Imagine if you could just go anywhere on Earth and you wouldn't have to worry about charging your batteries or where you're going to plug in, and just have energy no matter where you are.
Dr. Paul Jaffe is the lead engineer on the project. In 2019, his team set out to demonstrate a vital part of the technology at one of the world's biggest marine testing facilities. A prototype system to transfer power over long distances without using wires. Instead, the power will be sent as a laser beam.
So we have here today a 2 kilowatt laser transmitter, and we have a receiver that is made out of photovoltaics, similar to what you would find in a solar panel. And this is really a remarkable capability that unlocks all kinds of amazing possibilities. So the power beam itself is invisible and completely silent. The way that we can help show where it is with this $20,000 infrared imager. You can see the transmitter sending the beam over 325 meters to the receiver at this end of the basin, which converts that back to electricity for us to use. You'll notice, though, that you cannot see the beam if you just look without an imager.
The aim is to ultimately use a scaled-up version to send beams of solar energy collected in space back to Earth. The transmitter would be on a satellite, with the receiver down on the Earth's surface.
Imagine if we could take the boundless sunlight in space, send it effectively to the ground, to wherever we need it, whether it's a refugee camp, whether it's a developing country, places that are difficult and expensive to get energy to today. If we could do that in an effective way, it would be truly revolutionary.
But firing a giant laser beam at Earth from space might naturally cause alarm. So Paul's team have developed a safety mechanism and are testing it out today. The system should detect when something or someone enters the beam and instantly shut down. This solar circuit breaker means the technology could be used on a much bigger scale in the future. For now, though, Paul's team are happy to use the beamed electricity to make a simple cup of joe.
This demonstration has exceeded our expectations many times over. We are opening people's eyes to the prospect for this revolutionary technology.
As well as creating safe power beams, Paul's team have been working for 10 years on a prototype space solar module called PRAM. Its job is to generate solar power and convert it to a form of energy that could be beamed to Earth. To check that the module would work outside the atmosphere, the team simulated space inside the lab. Liquid nitrogen matched the extreme cold. A vacuum chamber removed the air, while xenon lamps mimicked the intense sunlight. But although space conditions are harsh, there's more energy available to harness.
In space, it's always daytime and it's always brighter than anywhere on Earth. So you not only have 24-hour-a-day sunlight, but it is also brighter. You never have to worry about clouds or nighttime or rain or anything that would interfere with the collection of solar energy.
The next step was space itself.
T-minus 3, 2, 1, and liftoff.
After more than a decade's work, in May 2020, the module launched aboard the US Air Force X-37B orbital test vehicle.
It almost felt surreal to think of how it started as just like a kind of crazy idea that we proposed and got the funding and resources and support to build, and finally made it to a point where we're actually launching it into space and it's operating on orbit and it's sending us data that we're now going to use to continue to push this technology forward.
Paul's team are laying the groundwork for a potential energy revolution in years to come. In the meantime, other solar technologies are already powering ahead. Solar towers capable of generating electricity 24 hours a day are appearing in sunny countries around the world. From Israel to South Africa. While advances in technology capture more and more of the sun's energy. In Australia, Raygen plan to start harnessing the heat from their cooling system to produce another critical resource alongside electricity.
That byproduct heat can be used to desalinate water very cheaply. And that produces the two most important resources that any community needs, power and water. With power and water, you can do anything.
Lightyear have plans for a car that's so cheap to run that billions of drivers would choose solar-powered transportation.
That became the mission of the company, clean mobility for everyone. That's what we're working towards. And first by making, unfortunately, a rather expensive car to test the technology to show everybody that this is working. And then the next step is to make it available to everyone to fulfill the mission.
And the spread of solar panels from land onto lakes and oceans is opening up an almost limitless opportunity to generate clean electricity from the sun.
I'm very optimistic. I think technology can provide the solutions, that we can develop this and that we can make this transition. It's doable and the technology is almost there.
When it comes to solar, the future looks bright.